No. I teach.
Yeah.
Do you need the board?
Luis, the board.
Do you need it?
Oh no.
Okay. Take my things.
Oh. Of course.
Oh, you saw me give a class too. Gelijk maken van
Is yours? Is yours?
Yep.
You try this.
reference frames. Maak je iPhone. Moet ik er wachten? Zo. It's from the system. We need to do it from within the system. Sonny, that's you?
No.
Is it not Sonny?
No. It has to be this script. This one.
Okay. Okay. So, happy that you're all here. That's the last talk in session 4. Professor Enrique Ferran, please. Thank you.
Okay. In this talk, we only are going to talk about detection of cosmic ray from the Earth, because with Maria Dolores, you have seen yesterday the detection from the space, the future planes. So, with what I'm going to talk about the biggest detector in the world for detection of cosmic rays at the ultra high energies. So I am going to, now we have to do an introduction to cosmic rays, and we are centered in the PRG project because you have seen yesterday the Gemeuso space mission. We have talked about the necessity to detect with the discovery of cosmic rays in 1962 by John Leslie of events with this Hugh energy, then the cosmic ray arrays of detectors were increasing, and also two techniques were developed. One from surface detector, putting some detectors for particles on the ground and in an array, each time bigger and bigger. And the other technique, it was to see the fluorescence of the extensive air shower secondary particles, the fluorescence produced during his travel through the atmosphere. Up to date, we have a lot of open questions on cosmic rays. First, what are the primaries? Which one is the composition, and from where they come from? Which one are the identification of the sources? And how do they get their energy? Which acceleration processes can give to a particle, to a small particle, this amount of this Hugh energy? And also, what do they tell us about the universe? Another way that it is under study is to use the cosmic radiation as to do astrophysics. Astrophysics in the sense to know the parameters of the sources or the possible sources, etc. If we can demonstrate which one are the sources of the cosmic radiation of higher energies. And also, if this cosmic radiation, we can use them as messengers from large distance in the sources to see what physical process are they working. This is a brief history of the experiments in cosmic radiation. As you know, at this moment, from previous talks, they were discovered by Balloon, and Balloon continue be using for detection of cosmic ray with films like photographies that are exposed to the particles, and the particles let the traces into registered in this photographic shield, and after you can recover and do the analysis of this, and this is the way, for example, it was discovered the antimatter, the first antimatter, the positron. In the satellite area, more or less at the 60, the 70, satellites were used to put detector for cosmic ray, mainly solid state detector or fluorescence detector, scintillators, and this kind of detectors. Put it in a satellite, and the satellite recoiling the cosmic ray, but because of the flux of the cosmic ray, these things, and also during flight, detector put it in the airplanes, in this kind of vehicles, may be used to during the flight catch the cosmic ray, but only we have explained before, only for low energy cosmic ray, mainly solar cosmic ray and the lower part of the energy spectrum of the cosmic radiation. If you like to go to higher energies, the flux reduce, then you have to put very large detector. This large detector cannot be allocated in a balloon or in a satellite or also in a flight, in a plane. So you have to put a rise of detector on the ground and to catch all the particles, secondary particles, that from the primary cosmic rays interaction arrive to the Earth by several millions or billions of particles in one extensive shower. Then the first, the kind of detector you can use is surface detector, detector of particles put on the surface a very large area, each increasing each to catch the higher energy of the cosmic rays, but also fluorescence detectors catching detecting the fluorescence emission of the atmospheric components as they are excited by the secondary particles of the extensive shower. And when you have all this technical for detection, normally you use in surface detector, you use scintillator, water Cherenkov tanks, and this kind of detector. But in most of them, you cannot separate the different particles in the extensive shower reaching the Earth. For example, you have a composition of gammas, electrons and positrons, electromagnetic particles, but also you have muons, you have protons, you have neutrons, etc. And they produce ionization, and you cannot separate. So you have a mixer composition. What you have to do to separate the composition, maybe some things. The first things we think to separate, it was, okay, we are going to eliminate the electromagnetic component. Then we can put plumbum, PV,
Plomo.
LED.
LED. Yes.
LED layer over the scintillator. Then the electrons cannot traverse the LED, and you only see, for example, muons. But what happened? You are not looking for secondary particles. You are looking third particles, because in the LED you have a mini cascades, mini showers produced by the electrons, a lot of them. So it is, and this shower produce electron. Then you don't have a clean signal only with muons. What is better is to put underground detector. Then in 3 meters of Earth, you can eliminate all the electron component, all the electromagnetic component, also gammas, and you only have muons. Then normally in this kind of detector, you have also put underground detectors to separate the electromagnetic and muon component that you detect in the surface detector, and by rest compare with the muon detector underground, you know the amount of muon and the amount of electromagnetic particles in the extensive shower. And this is important because of, to obtain composition, because electromagnetic particles in the extensive shower generate only electromagnetic particles, that is, photons, electrons, and positrons. But hadronic primaries also generate muons and protons and neutrons. So, to separate gamma rays and electron cascades from hadronic cascade, you have to know if in the shower you have or not muons. In fact, a proton primary generate a lower level of muons than iron, for example. So, independent of the amount of muon, you can know the atomic number of the primary cosmic rays. You can start. Another particles are more evasive, neutrinos. And neutrinos are produced in the atmosphere, as we have seen before yesterday, and are part of the extensive shower. So only, so we can also add underwater or ice detector to as another technique to detect cosmic radiation. The technique you can use surface and fluorescence detector, and you have a hybrid detector arrays like OYE that has two detectors, the surface detector and the fluorescence detector, and use both of them. After the construction of the Pierre OYE, we start to put more detector to detect more components of the extensive shower. And for example, we include radio and microwaves analysis, and all of them are analyzed together as a multi-parameter or multi-messenger analysis to obtain most of the properties of the cosmic ray, or the primary cosmic ray. Okay, this is the area covered by the Pierre OYE, 3,000 kilometers squares. For example, if you put in the city of Milwaukee, you cover all the city area and part of the Great Lake, and is a very large area filled with detector as a surface detector, as a unique surface detector, and this is the place when the Pierre OYE is installed. Is here in the Mendoza province, near a city that is the name is Malargüe. In this city, there are all the
a small big town, let's say.
Sorry?
Small town.
Yeah,
so,
it's a
I mean,
small
a city
yeah.
called Malargüe city. It's a
yeah,
small town.
It's a small town.
Say.
Really, the town was start with the people of the petrol companies, because there are petrol in this area of the Pampa, and these people create a very little village to be during the prospection works for to have the petrol and gas, natural. So, but now here we have the the central data acquisition machines. All the signal over these 3,000 kilometers are collected by radio in the 4 telescopes, fluorescence telescope that are in 4 mountains, small mountains, to be higher than the flat surface detector. And in this building, you have each one, you have 6 telescopes covering 180 degrees of field of view altogether, looking over the sky over the surface detector. Then, when you have when a cosmic ray arrive, the extensive shower cross the atmosphere over the surface detector. The particle generate fluorescence that it collected in the telescope, in the fluorescence telescope in the building, and after the particles of the secondary particles that reach the Earth, inside in the heat the tanks and give a signal, Cherenkov signal in the water of the tanks, and this signal is collected too. Then you have a lot of information that you have to send by radio to Malargüe. And in Malargüe is collected the data and stored and sent to 2 mirror repositories. One in Lyon, in France, and another one in Chicago, in the US, to store the data permanently. And one, it was in America, because all the American people can access the data easily, because Malargüe have a very poor, when we arrived to build the detector, has a very poor connection with Buenos Aires. And we connect with a fiber. We have a special project to funding the connection between Malargüe and Mendoza, because the data, because we don't have enough speed of transmission. We cannot. We don't have enough transmission speed for transmit the data to this server. It was one of the main problems. So, European project financed this connection. Okay. In the middle of the area of the surface detector, you have rivers, you have cows, you have ¿cómo se dice? Cabras.
Goats.
Goat. You have goat.
You have all kind of animals.
Yeah.
You have spiders.
You have not
Yes.
You have not agriculture. You have animals. Mainly. You also have a problem. The spiders named I don't know in English, Viuda Negra.
Black Widow.
Black Widow, yeah. Black Widow. Okay.
And we don't have enough hospital close enough.
Yeah.
So it's a big problem.
It's another one that the name is K7 is more dangerous than Black Widow. If you have a bit of this K7 spider, you only have life for your life is for 3 hours. But the closest hospital in Malargüe is at 5 hours in San Rafael.
San Rafael.
So you are dead if you don't have the antidote. And for Black Widow, you have 7 hours, something like this. So you can reach San Rafael Hospital. Okay. Here you have 1,660 Cherenkov tanks with a separation of 1.5 kilometers. All them are connected with the central, and when you are going, for example, to Loma Amarilla, you have 80 kilometers traveled by not asphalt road, only sand and stones and these kind of things. So if, for example, you can have a problem and the worker have a lot of problems, you can have a problem here, for example. Here you can only find horses, cows, some birds, these kind of things. What you have to do, you have to go with a radio, but if radio doesn't work, what do you think you can do to send the signal that you have in a problem? What do you think? There is a way study to do this, because of people can we work here. I have been alone work by this area. Nobody knows. Then you have to radio to say I have reached the working place. But if your radio, for example, go out for batteries, what do you do in this case? This is a solution.
Like a cosmic ray, you use the Cherenkov tanks.
Yeah, you use the Cherenkov tanks, and you have to access the battery and disconnect the Cherenkov tank. Then an alarm arrive to the central data area office in Malargüe, and they come to pick up you. Okay. Another problems you see here this yellow line, a separation, but it's a river by here. Here is a river, and you have to put each tank in an exact position. Well, we do it this one, but in spring, when the Andes mountain, the ice goes in water, the river, the phreatic level of the rivers increase, and some tanks are moved by several kilometers. So then you have to have permanently a working group taking care of all these instruments. And this is expensive, and it's financed for all the people and all the countries in the collaboration. Okay, this is a simulation of what happened when, for example, one protons of 10 to 15 electron volts arrive to the atmosphere, and have its first interaction at some altitude. Here the first interaction altitude was 22 kilometers and a half, more or less, and start to generate all these particles of the extensive showers. One of them are hadrons, other muons, by color in the simulation you can see, electron and neutrals. Okay. Then the particles arrive more or less in a front to the detectors, and you simulate that the front is a plane, and when the plane arrives to the detector, you register the intensity of the light and the time at the level of the nanosecond. Then, if this is the front of particles, they come all together in a thicker layer, and if you can obtain the direction of incidence of the primary cosmic rays because of the time. For example, if the particles come in this plane and the detectors are in this plane, they hit first these detectors and after this detector. With the time, the difference in time, you can, with 3 tanks, we can obtain the direction of arrival of the primary cosmic ray. Okay, if you have more, better, but at least you need 3 detectors with sigma.
The axis is kilometers or meters? Meters, right?
This I think is meters, because this is a low energy. This is under the threshold of. It is only a simulation. This is under the threshold of Piaget. Piaget is at 10 to 17, 17.5 or something like this. This is a low energy cosmic ray. So, for example, the first detector in which Maria Dolores tell us he do his PhD work was Hydra, that was 200 by 200. Only one things like this. Okay, and the detection, the detected cosmic rays were of this energy. Okay. Okay. Here you have the position of each tank, okay, and the position of the fluorescence telescope. Each tank is a water tank with 12,000 tons of water, filled with 12,000 tons of water, with 3 photomultipliers, and with surrounded by TVEC. TVEC is a special, very large refractive layer material, 99.9 of reflection. Then, when a particle inside in this water, by Cherenkov effect, we learned the other day, generate Cherenkov ultraviolet light, and finally the Cherenkov light reflect in the TVEC of the borders, and up to finally are incident in one of the photomultiplier. The light of the photomultiplier is recovered and the data is sent, the data or the intensity recovered is sent to the central office in Malargüe by radio. Also, another problem we have with the transmission of the signal, it was that as you have a lot of detector emitting in the wideband of radio, sometimes the transmission system of the signal collapse, and we have to move to another band, to wireless and this kind of things, to microwaves. Okay. But well, these are the buildings of the Cherenkov of the fluorescence telescope. Each one of these windows is open in the night. There is an automatic system that detects the amount of light, because during night with moon, you have to close the window. It is in front of it is receiving the light of the moon, because the light of the moon burn the photomultipliers in the telescope. Imagine the light of the sun. In fact, there was a problem once time, and one of the windows don't close in the morning, and they have to collect the photomultiplier from the ground, because the photomultiplier were flown, were go to liquid. No sé cómo se dice.
Drown.
Okay. Well, this is what happened. You have seen in a previous, this is a part. You have here the tanks, and the extensive air shower emits the fluorescence light, and the particles reach the detector that here is are put as lining detector when they did. And during the night, you can open the telescope and register the light of fluorescence that particles traversing the atmosphere produce. Well, with this, you have two signals independent. One of the fluorescence, and the other one, the particles registered in the surface detector. And you, what are doing is combining. Okay, let's see how it works inside the Cherenkov tank. If we go inside the tank, we see the water, the photomultiplier, when the particles of the shower generate Cherenkov light, and finally the Cherenkov light are recovered by the photomultiplier, and the signal, the data are transmitted by radio to the Malargüe village, that we have the office of the central data. In the Fluorescence telescope, each one you have a mirror. Here another one, and here is the camera. Then the light of the fluorescence inside or in the mirror and hit the photomultiplier. Here you have 550 photomultiplier for each telescope. Okay. the mirror are with the curvature magnifying the area, the field of view that you have to collect the fluorescence light. The fluorescence light is very small. In fact, very thin. In fact, you cannot see with your eyes. So the photomultipliers are very sensitive. Then, if the light of the moon or the light of the sun enter to this without the window block, the temperature may be some 1,000 Kelvin inside, so destroy all. Okay, let me. Okay. Now we are going to pass for what are the reasons to build so high detector. What we are going to obtain. The detector cost, it was more than $100 million, more than. But not only this is the money you have to spend. Each year you have to maintain all the electronic working properly. So, and this kind of thing that I tell you happened, a tank that floated, go river, guided by the river. So, and all this thing happened, and you have to move again and to put, and also the construction. Okay, the objective of the PROJ were measure the properties of the cosmic ray above 10 to 18 electron volts with unprecedented statistic and quality, and obtain three main topics: energy of cosmic ray, origin of cosmic ray, and composition of cosmic ray. For the energy, obtain a very well energy spectrum at the time that PROJ start his building and was approved. There were two experiments that were telescope array y AGASA, and in the spectrum, AGASA, after the uncle, the spectrum for AGASA, it was increasing. This was the measurement of AGASA. The other experiment was a telescope array that give the measurement that the spectrum decrease. When you have to experiment giving different results, you have to put more experiment, a better experiment, to know if the spectrum increase, like set AGASA, or the spectrum decrease, set telescope array. Finally, Oye find that the spectrum decrease, and also establish finally the GCK effect is there and is working, but at this moment it was a problem because you don't know what happens more further than with the extragalactic component. This was the other in the energy, the other topic, the determination of the GCK effect existence, because of this that I have tell you, and exploration the second knee and the ankle region, because at this moment there was enough statistic to to know if the second knee is there and how it was the ankle. If the ankle was with a increase in the flux or a decrease in the flux, because you have two experiments telling you both things. The origin. This during the 20 years of life of Piaget, we have obtained a better energy spectrum. We have determined that the GCK exists, and we have exploration and proof that we have a second knee and an ankle. But the origin, up to now, is not discovered, it's not demonstrated. But by the moment, it was one of the first objectives was where the ultra high energy cosmic ray come from, and if there is anisotropism. About composition, the objective it was to know what are cosmic rays, and also search for photons. I have said the previous day that the universe becomes opaque to transmission of gamma rays. So one of the topics was to search for photons and also to search for neutrinos. But this moment we don't have ice cube, so we are looking for neutrino. And at this moment also we have looking for neutrino period, but zero candidate at the moment. What happened with the particle physics at 10 to 19 electron volts? We are going to see that we have obtained cross section for these energies of proton-proton interaction, and related as a secondary effect of all this instrumentation, you have been several studies of solar activity influence on the tank. There are several works that study this 11 years periodicity of solar activity in the tanks, and also the effect of transient in the atmosphere, thunderstorms, and these kind of things are seen as a signal in the tanks. There are few works. It is not the main objectives, but are secondary objectives that some of the researchers have spent his time to do this kind of very curious result they have obtained. Okay.
Did you measure ultra high energy photons?
Sorry?
Did you observe ultra high
No.
energy photons?
No. At these energies, there are no gamma rays because of the universe is opaque. Okay, and the level of detection is only that Piaget have been performed is only as you are obtaining more time measuring, you only can put limits, under limits or constraints to the detection of photons. Okay. Okay. Then Oye has two detectors, surface detector and fluorescence detector. But new signal in the cosmic rays in the extensive shower appear. And we have some upgrades, a lot of upgrades, to increase the possibilities of the PROJ observatory. The first one was the high elevation Oye telescope. Now I am going to show you what each one is, but now I like to list of we develop, because you see a lot of tries to detect better and with more parameters the different component that are in the extensive showers. Aera, to measure the radio signal generated from the Earth, EAS, extensive showers. Amiga is an infill that like to reduce the umbral of detection of PROJ to reach the second knee zone of the spectrum. Batata is a telescope to obtain the punch through where the altitude where the muons are generated, the muons that reach the surface of the Earth. Amber is to detect the microwave Restralum radio emission from the particles of the extensive showers. Midas is more or less the same. ICE is also electron radiometer, and the last one it was Oye prime. At this time, before Oye prime, the PROJ collaboration, the think about that is not good, put effort in a lot of upgrades and decide to only go on with Oye prime, that it was selected after a discussion inside the collaboration. Okay, let's start with HIT. HIT, try. Okay. You have this surface detector, and above the sky of the surface detector, you have the surface fluorescence detector to see 30 degrees aperture the sky over the surface detector. Well, to catch lower energy cosmic rays that interact upper in the atmosphere, we put these three detectors looking 30 degrees above the fluorescence detectors. Then you have the surface detector. Over the surface detector, the sky you are monitoring by the fluorescence detector, and HIT try to detect the extensive show were produced by particles upper this part of the atmosphere, that are particles with low penetration level and with lower energy. Okay. Aera is an radio array. These are the antennas they put in the ground near the, for example, here you have a tank of the surface detector, and separate in between the surface detector area, they put an array of antennas to obtain the radio signal of the extensive air shower generated by the extensive air shower particles in the atmosphere. Amiga is trying to measure the lower part of the spectrum from Oye start at 10 to 18, and Amiga try to go down in the energy up to 10 to 17.5 and up to 10 to 70. For this, what we have to do is to put a more dense area, a hexagonal area of tanks, and we include the green tanks, one in between both of the OJ tanks, nominal OJ tanks. Then, if between blue tanks you have 1.5 kilometers, between with this field of tanks, you have only half of the distance between tanks. As the energy is going down, the flux is going up. Then with this area, you have enough area to detect enough statistical number of showers with lower energy. And this red in field is to reach the 10 to 17 electron volts. It's again to put a tank in the middle of the distance of both of two tanks of the other infield. Then the separation of the tank is the half again of the half of the OJ standard. With Amiga has two parts. One is the infill. It was the first what we built, because you only have to put more tanks with the same technology. But the other is to put close to this more dense area with tank of SD detector, to put underground muons. For each tank, you put a lot of square meters of planes with ventilator at 3 meters underground, covered by the land. For example, this biggest detector are 30 square meters area. This other one are 20. Then you have here, around the surface detector, you can measure all the particles in the extensive air shower reaching the Earth, electrons, gammas, positrons, and muons, and also, of course, a little amount of protons, etc. But in the underground detector, you have only signal for muons. Then you can obtain how many muons component has in your extensive air shower. So you can obtain if it's a proton, or if it's a carbon, or if it's iron, on depending of the amount, the relation between the muons and the electrons. Okay? Only taking the difference in the signal. This one, the other one, Batata, I was involved in this detector also. Batata is like Amiga.
In Amiga too.
Yeah,
In Amiga we were
Yeah, in
funded.
Amiga.
We contribute.
Yeah,
In Amiga.
in Amiga also. I forget to say. Okay, the idea of Batata is to put some 3 layers of scintillators to obtain the direction of incidence of the muons. Okay? With this, you can reconstruct the direction of arrival of the muons, and if you have here detected by the surface detector, you have here the core of the extensive air shower, the center of the extensive air shower. With the direction of muon, you can obtain the altitude where the muons are generated, because most of them are generated at the same altitude. Okay, at least what arrived to the Earth. Okay. For this experiment, what we have to do first is, as we are in the Pampa, we need to power all the instrumentation. So we need to mount, and this was financed by Spain, and we were installing and providing all the materials. We put several aerogenerators to obtain power from the wind, and also a solar panel station. We put four aerogenerators that giving us 4,000 watts of power, and a solar plant with 5,000 watts of power, all with batteries and with a container when we have the control room of the experiment, and etc. etc. This is the area. This is the, well, this is me. This is the area. These are the aerogenerators installed. This is the antenna for telecommunication. These are the solar panel, the container with the electronics, and another smaller container with the batteries. And this was the installation of the scintillator planes in the hole at 3 meters of profundity. After we filled with all these sack of grounds inside the scintillator. Amber was this antenna for detection of microwaves generated in the extensive air shower, and well, okay, you see here another robot, another telescope that is Midas, is for the same, is also for microwave detection, and Oje Prime. When we finish to build Oje, to separate electromagnetic from muonic component of the extensive air shower, you think about to convert the surface detector that you have seen before in the video to convert in only one detector that measure all these things that we have made research and development with this upgrade. And we put a layer to measure with a protection to measure the muonic component in this layer and the electromagnetic and muonic component in the water tank. So we have to obtain both population and the relation between the ratio between number of muon and number of electron and gamma measure. Also an antenna to like AERA to measure the radio signal, and this is what have been done the last year in the period to convert all the surface detector into this OJ prime detector to improve the signal and to compact the signal in only one detector. Okay, let's go then. I don't know the time.
Son las 3:15. Yeah.
Ah.
Yeah. You go
Yeah, finish. No, not this. No.
directly to the
Okay.
end, or you
Okay. We have seen the objective are the energy spectrum, the composition, and the radial direction. Then, Pierre Auger obtained this energy spectrum, state and demonstrate and measure the position on the ankle at this energy, also the GCK at this other energy, and demonstrate that the GCK act, that we have the GCK effect, it's working in the cosmic radiation. This is a spectrum where the nominal OJ are the blue circles and the Amiga signal is the red circles. As you see, there is a good agreement in the mix in the middle of the detection, and we have to increase the spectral response of the detector. We decrease up to 17.5 in the logarithmic scale of the 10 to 17.5 electron volts. For composition, we have seen that when you go to higher energies, the composition change from mainly proton composition. That you see the red line are pure proton composition studies.
Luis, probably here you need to explain the X max. What means X max?
Oh yes.
You have to explain here. Probably in the board you can
Yes.
explain better X mass. What is X mass? This is a very crucial parameter for composition studies.
Yes.
So,
When you have
borra. Tienes que borrar.
an extensive shower, the extensive shower is traveling the atmosphere, and first you have a few particles. You have a few particles, and the number of particles increase as you are crossing the atmosphere. But reach in a moment, this behavior change and start to decrease the number of particles. to reach the ground. Okay. Then the X max parameters is the atmospheric depth
for
maximum number
of
of particles. This is X max. What happens if you have a proton? Let me take another colors. If you have a proton, the proton interact and produce less, and the X max produce deeper in the atmosphere than for a proton than for a iron, for example. If you have a carbon, for example, you have a intermediate behavior. So with the X maximum parameter, you can do you can obtain composition. Okay, and this is the parameter that you have to know how it works. Oh. Here. That, for example, this is the X max, and for protons, the depth must be this line, but for iron must be this one. Okay, then at lower energy, most of the cosmic radiation are protons, but when you increase the energy, the composition goes to iron. It's heavier. Okay, and this is the same with all the parameters. You see, for the for the higher energy, the composition goes more or less to heavier composition near to iron, and it repeats in all the different forms to measure the X mass. Okay. Then when you are going to higher energy, protons start to disappear, and also because the GCK. But GCK don't affect in the same way or in the same energies to the iron. So only remain the heavier cosmic ray, because they disappear the protons because of the GCK effect. Okay. Neutron search. No, we don't have found any estes of neutron. This is normal. This is expected because neutron only life, the mean life of the neutron is lower than 1000 seconds. Then the sources of neutron must be very close to see the neutrons alive. So close that they have to see in the solar system, more or less. Then, of course, it is normal, but this is a comproval of you don't have any source of neutrons near the Earth. Neutrino search. Neutrino search. We are looking for neutrino. The probability of obtain one of detect neutrinos with OJ at this moment it is about only 1, and we have no candidate for ultra high energy neutrinos. we look for neutrinos. This is a regular shower. Then what we look in the data is other 4 kind of detection of neutrinos. For example, a deep shower that starts very near the detector, because of the neutrino have a very low probability of interaction and cross the atmosphere, and normally cross the detector and don't give. But perhaps someone can have a first interaction point very near, a low altitude very near the detector. Another possibility is outgoing neutrino. Neutrino that reach the Earth, decays in a tau neutrino, and this tau neutrino generate a cascade that the detector it can see going up. Okay, then the signal is very different of the normal signal of a regular shower. Double cascade produced by a neutrino that decay in a tau, and the tau decay in a neutrino, then produce 2 showers in the same event. Okay? And neutrino that, as Argentina has the Alpes, the Andes near, and a neutrino interact with the material of the Andes and produce a tau, and the tau can produce a shower that can be detected by PROG, but zero can detect. And well, this is the Hillas plot Maria Dolores showed yesterday, but here you have. Do you remember in the plot she shows yesterday? You have this line, and you don't have sources to accelerate protons to 10 to 20 electron volts. Okay, but this is the line to accelerate iron up to 10 to 20 electron volts. And as you can see, we have several sources that can accelerate iron but not proton. This may be another reason, because of the spectrum becomes heavier at the highest energy. Okay.
So you mean to say that accelerating iron is easier than accelerating a proton?
Yes, because the force for the acceleration is multiplied by the atomic number 26. Then you need a source 26 to 2 or 1 order the magnitude lower than for accelerated protons. The acceleration depends on the acceleration you can produce depends on the charge of the particle. And iron is 26 more charged than the protons. So in source that you cannot reach these energies for the protons, you can reach these energies for iron.
Yeah, the acceleration is inversely proportional to the mass also. Is it?
Yes, but mainly is a relation between the charge and the mass.
Okay.
It's not exactly 26 times, but this is what happened. Okay. Here you have 69 events with more than 55 exaelectron volts energy. We can remember again which is exaelectron volts.
No, we have already.
Okay, we know now. The horizon for PROG is 100 megaparsec. Then we have to find sources in lower distance than 100 megaparsec. Here there is a in the catalog we filter to sources at lower distance than 75 megaparsecs to find sources. And you have here the 318 AGN of the catalog in the dark point positions, and each blue circle is the detection of one of these cosmic rays in the periods. So there are several positions of the universe where you have more population of events, but mainly we were looking for Centaurus A because we have a lot of detection, a lot of events detected around. The circles are big because of the errors in the deflection. This is the problem of to use protons as detector of sources. Okay. Here is the study of the Centaurus A as one of the sources, but it showed that only 7.6 events are for isotropy are expected in this direction of Centaurus A. We obtained 19 events, but this is not enough statistic to say that Centaurus A is one of the source of ultra high energy, the most energetic particles of the cosmic rays. We obtain, as I have said to you before, we obtain the cross section for proton air interaction, and we obtain and compare with that obtained by the LHC, the accelerator, and the other experiments data. And one unexpected results that made that we have to revise all the simulation models of the cosmic rays interaction is that we find more muons production in the extensive shower than Monte Carlo predicts. Here you see several Monte Carlo. If you make calculation with iron, with proton, the number of muons with respect to the protons one take up as the unity. In iron you produce more muons, but the different methods, the measurement on the number of muons you see here, this cloud of data is upper the iron and upper the proton expectation. So we don't know what happened in the models and in the physics at this high, very high energy that produce more muons that the Monte Carlo predict. Now there is a revision of all the Monte Carlo interaction that may not work in the same way at accelerator energies that are higher energy up to 10 to 90, okay, 10 to 20. Okay, as a summary, what we obtain as a result of the PROJ at the moment is the GCK is confirmed, the energy spectrum has been obtained with unprecedented statistics, there is anisotropy in the arrival direction, but no sources clear at the moment. The ultra high energy cosmic rays are hadronic and no photons. And you have a heavy composition at the highest end. The neutrino and the photon limits of observation are in accordance with the GCK suppression. We have obtained also the cross section of proton air at 57 exciton volts for the first time, and we obtain a higher muon contents in the extensive shower than predicted by the physics used by the Monte Carlo models of prediction. Yes?
So what would be a possible explanation for the discrepancy in the muon content?
The muon in the extensive shower?
Yeah. What were the suggested solutions for that?
I don't know all the solution suggested, because you know that when this kind of thing happen, a lot of people start to think about solution for this problem. One of the first thing about is that all the Monte Carlo models, what they do is to extrapolate the cross section measured at lower energies. You extrapolate what will be the cross section to the higher energies, and you made this extrapolation in a way. You expect that this work. Probably at higher energy, the cross section don't behave as a prolongation of the cross section at lower. This may be this is the first thinking about. The problem is you have to measure the cross section to be sure the behavior at higher energy, but you don't have accelerator to measure this cross section at so high energy. So what we have to do is look into the data, obtain the cross section of the interaction at this high energy. To modify the Monte Carlo to obtain what we see. But this is not good, because this is not an explanation. This is a reparation of something that is not working. You are not going to know why not work. Perhaps maybe a problem in the detection techniques. By the moment, it's not solved. Only we have performed theoretically a universality method that what do is to move the number of muon of the Monte Carlo to the high. Then we solve the problem, because now the Monte Carlo is in agreement with the data, but this is not that solution. We have to
all energies, or just above a certain energy?
At higher energy.
Higher energies, yeah. So lower energies, the
low energy physics is working well.
It's working well.
But up to accelerator measurement. So what we first think is that the extrapolation of the cross section we do for the models is not good.
What energies start the discrimination?
Can you go to the plot, please?
Oh. Here you see that the study are for highest.
Very high, okay. So it's above what you can reach in accelerator.
In accelerator.
Yeah. You cannot reach. So it's a difficult problem to solve without acceleration that reach these energies. And also perhaps this prediction is not so good. Okay.
I mean, the systematics and the
Yeah.
are not bad.
Also, you think that in cosmic rays there are a lot of systematical errors because you are using the atmosphere as a calorimeter, but the atmosphere is very changing. So also in the different part of the surface detector, the atmosphere parameters may change in the 3,000 square kilometers. So it is difficult, and we have under a lot of systematic errors and statistical error also because we don't have too much flux. You only have here 69 events at this end, so it's not too much. Okay. And also the deflection gives you a circle higher than we need. Okay. Okay, then this is all for my. I don't know what time is it. I think it's enough. If you have some more questions. Yeah.
If you can accelerate the iron to 10 to 20 electron volt, why you can accelerate the proton? I mean, if I have 2 atoms of iron, yes, to an energy of 2 to 20 electron volt, and they face each other, this doesn't make that doesn't make out a proton with the same energy.
You mean, for example, when you have an iron of 10 to 20, some interaction, and the result will be a proton with 10 to 20. Or no? You mean this?
Yes.
No, because when you have one iron with 10 to 20, you have 56 nucleons, and the sum of the energy of all these particles in the nuclei are 10 to 20. If you extract a proton of this nuclei, you only have one proton of 10 to 20 divided by 56. Okay, as much. If you don't lose energy extracting the photon, okay, then it is very difficult to obtain a proton of 10 to 20 from an iron of 20. Normally you lost some energy that is each share in all the nucleons. More questions?
Are there any further questions?
Okay.
No,
let's thank the speakers for the
Well, before we go, I'd like to give the speakers a small
token.
present token from the department.
Oh my
Please
God.
come.
Oh,
So
Very
this
small.
mark was the design of the department.
Oh,
It says that influencing tomorrow
oh,
today.
thank you.
thank you very
And
much.
also for you.
Oh,
This
For the coffee.
you have no time for this.
Coffee, tea.
Chardonnay.
I am more,
Chardonnay.
I am more
I'm
the
sorry.
coffee, but
Can
the
you
coffee.
translate, please?
They are high price.
Influencing tomorrow today.
Influencing tomorrow today.
Yes.
It's your
That's
logo.
the slogan of the
Slogan of
university.
Oh my goodness, it's true. It's full. It's completely true.
Okay.
Yeah, okay.
Okay,
See?
So
Thank you
thank you
very
very much for this series, and
And this is the logo of the
hope to see you
university.
again.
Yes. This is the 2 letters for Bar Ilan.
Ah, very good.
Right. So
Thank you very much.
Thank you. Thank you all for coming.
thank you all for coming, and hope to continue with this tradition.
This is for us. Huh?
Yeah. Thank you.
Important.